Hey everybody, Dr. A here, and in this video we're going to be exploring another example of average shear stress. So let's get started. In the given information, we're being told to compute the member forces in the truss and the shear stress in the pin at A, which is in single shear and has a diameter of 0.25 inches. So let's take a look at this truss that we have. We have a pretty simple 3-bar truss that's subject to a 600-pound horizontal load at C. We have an external pin reaction at A and a roller at B. The vertical dimension is 4 feet and the horizontal dimension is also 4 feet. That means that these interior angles are 45 degrees, right? A 1-to-1 ratio gives us 45-degree interior angles, okay? So this will be a nice little review for those of us who are maybe a little rusty with your truss analysis procedures from statics. So let's go ahead and get started. Under the solution, I'm going to start by saying, let's use method of joints to compute the member forces. Okay, method of joints comes from statics, and basically what method of joints says is that when you have a truss, you start at a joint that has at least one known force. In this case, joint C has the known force of 600 pounds, and at most 2 unknown forces. How many unknown forces do we have at joint C? Well, we have the force in AC and the force in BC. So we have 2 unknown forces at joint C. So we can start our method of joints analysis at C. Could we start at A or B right now? Well, the answer is no, because right now there's nothing known at A and B, and we have too many unknowns. We have more than 2 unknowns at A. In fact, we have 4 unknowns at A because that pin reaction has its own 2 unknowns. And then we also have FAC and FAB, which are 2 more unknowns. And there's 3 unknowns at B. Now, if you remember from method of joints, what you could do is you could solve for these external reactions. You can get AY and AX, and you could get BY, then you would have enough information to start at either A or B. But the great thing about method of joints is that we can start at a joint that is not a reaction, in this case joint C, because we have 1 known force and we have at most 2 unknown forces here. So let's go ahead and do that then. We're going to say free body diagram of joint C. And when we do that, we're going to draw this 600 pounds here. And then we're going to have FAC, and then we have this unknown FBC, right? And then that's at 45 degrees. And so we're going to apply 2 equilibrium equations because a joint and a truss is a particle. And from particle statics, we know we have 2 equilibrium equations we can use. The first one is going to be sum of the forces in the x direction equals 0. So we're going to say 600 pounds plus FBC times the cosine of 45 degrees equals 0. So FBC is going to come out to be a negative value. So we're going to say 600 divided by cosine 45. We get 848.5 pounds. Now, what does that negative mean? That negative means that that member is in compression, 848.5 pounds in compression. You can also say that it means that that 848.5 pounds is actually pointing at the joint, okay? So in our free body diagram, we assumed it was pointing away from the joint. We did a calculation, it came out negative. So FBC is actually pointing at the joint, okay? So that's how, nice little review of how we can think about this from method of joints. Are we done yet? Well, no, we need to say sum of the forces in the y direction equals 0. And so here we're gonna say minus FAC plus 848.5 pounds times the sine of 45 degrees equals 0. Why positive here? Well, from our previous step, we figured out that because FBC is in compression, FBC is pointing at the joint, which is really pointing into quadrant 2, which has a positive y component. That's why this comes out positive, whereas in the previous step, we yielded a negative number, okay? So again, nice little review of method of joints. So do some rearranging. FAC will be 600 pounds in tension, okay? Are we done? Not quite yet, but we're almost there. We knocked out these two member forces. We need the last one. We need the force in AB. So where should we go next? Which joint should we go next? Remember the criteria. We need to go to a joint that has at least one known force and at most two unknown forces. So joint A is out of the question right now because we still have too many unknowns. We have three unknowns, right? You have AY, AX, and FAB that you all don't know those, okay? So the next joint we go to is joint B. We have one known force. What's the known force? It's the force in BC that we just figured out, okay? It's this force here. And what are the two unknowns? FAB and BY. So joint B is our next candidate, all right? So we're gonna say free body diagram of joint B. And then here we're gonna draw BY there that we technically don't know yet. And we don't know, I'm sorry, we do know FBC. So this is FBC is 848.5 pounds. And then what we don't know is this should be FAB, yes, FAB. And we know that this is at 45 degrees, okay? And remember, FBC was in compression, so when we're looking at joint B, that's why it's pointing at the joint. It's pointing, is equal magnitude, opposite direction from the free body diagram we saw earlier, okay? So here I'm gonna say sum of the forces in the x direction equals 0, and I'm gonna say minus FAB plus 848.5 pounds times the cosine 45 degrees equals 0, okay? And we do some rearranging, and we'll get FAB as what? Well, we should get 600 pounds in tension, and you can just double check that by punching that into your calculator. But, you know, you're at a 45-degree angle, so it should take you back to 600 pounds. And it'll be in tension, okay? So our three-member forces, if we want to summarize them, are FAB is 600, not 800, 600 pounds in tension. What else do we have? We have FBC is 848.5 pounds in compression. And what's the last one we had? FAC, which is 600 pounds in tension. So that's part of our answer. Now, the other part of the problem said compute the shear stress in the pin at A. So we're going to say pin A. And so this is going to be a shear force divided by the cross-section area of the pin. Now, the cross-section area is easy enough, right? That's pi d squared over 4. So that's going to be pi times 0.25 inches squared over 4. And so we can easily get that cross-section area as 0.0491. 0.0491 inches squared. So we need that. But what about this shear force V? Okay, how do we get that? Well, let's think about what's happening at point A. I'm going to go ahead and check off AB since we got that force. But we need to get the shear force at point A. So the question is, how do we get that? Well, the shear force at the pin A, the force that's causing a slicing or shearing effect at A, is going to come from the force in AC and the force in AB, both coming into that point A. So if I zoom in and I say, okay, what's happening at point A? Free body diagram of A. All right, what's happening there? Well, we could have an AY there. We could have an AX, which technically we don't know right now. All right, but we also have what else? We have FAC and FAB coming in there, all right? So FAC is right here. This is 600 pounds, and that was in tension. And FAB is this 600 pounds, also in tension. And so guess what? AY is going to be equal to 600 pounds. Why? Well, if you sum forces in the y direction, AY must be equal to 600 pounds. Similarly, AX is also 600 pounds, because if you sum forces in the x direction, the value of AX that balances this 600 pounds should also be 600 pounds in the other direction. And so finally, how do we get this shear force out of this, right? We're going to say the resultant force, FRA, is the shear force that we're looking for, okay? So how do we get FRA? FRA is simply going to be coming from the Pythagorean theorem. Look at this. You've got a right angle right here. You have a vertical force and a horizontal force. And so you're going to combine them using the Pythagorean theorem to get this hypotenuse here, right? So it's going to be 600 pounds squared plus the other 600 pounds squared. And then, of course, you take the full square root of that. So FRA equals what? Let's punch that in our calculators. 600 squared, and then we really just multiply that by 2, and then we take the square root of that. And so guess what we get? 848.5 pounds. Look at that. Sounds like a familiar number to me. And this is the shear force at point A that we're going to use to calculate that shear stress. So finally, tau at the pin at A is 848.5 pounds divided by 0.0491 square inches. And remember, that pin was in single shear. That's why we're not dividing this by 2 like we might do in another problem. Okay, divide by 0.0491. And so we get 17,281 psi. If you want that in ksi, you can say 17.28 ksi as your final answer. And that concludes this example. So if you found this helpful, please hit like and subscribe, and please be on the lookout for other videos with similar content. Thanks for watching.